All right. Thank you very much. Good afternoon, everybody. My name is Gabe Rogers. I will be talking about guidance and control of an interstellar spacecraft. Just to give you a little bit of my background, I am currently the Deputy Mission System Engineer, Spacecraft System Engineer, and Guidance Control Lead for the New Horizons spacecraft. I was also the Guidance and Control Lead Engineer for the Van Allen probes during INT when they launched and for the first few years of the mission. So I've got sort of a unique ability to have seen a spacecraft that is going out of the solar system, and also a spacecraft that has long flexible wire booms and some of the dynamical features that we would expect to see from a spinning interstellar probe spacecraft with deployable booms. What I'm hoping to accomplish today is to convey some of the capabilities of a notional guidance control system and how that particular system would enable or dissuade the use of some of the more inventive science instruments, communication systems, and trajectory options that have been sort of thrown about this week. These are things including wire booms, optical communications, a Sun Oberth maneuver, and stuff like that. I'm not saying that guidance and control can't facilitate these types of things. I just want to try to present what the challenges are and what we need to look at when we're designing a system. I'm going to discuss some of the challenges for designing a system that's supposed to last 50 years, why it's a bad idea to have certain pieces of hardware, and discuss some of the concept of operations that we have for the different trajectory options. So for Interstellar Probe, we've basically been discussing what the possible configurations are for now. And each of these directly impact how we would design a guidance control system for the spacecraft. The GNC hardware algorithms and concepts of operation are dependent on if the spacecraft is always spinning, or if it's a hybrid with a dual mode spacecraft, or if it's always 3-axis control. The science payload chosen directly determines how we design our guidance and control system. So whether or not we have wire booms, fixed rigid booms, deployable structures, deployable instruments, gimbals on the system, all of that drives how we would design a guidance control system. The trajectory option, whether to fly unpowered Jupiter gravity assist, whether to have a powered Oberth maneuver at Jupiter, and then with the gravity assist, or to have a Sun Oberth maneuver, all of that also affects the design of the system. And we're going to, this presentation is going to focus on the challenges from each of these, from basically controlling a 3-axis spacecraft at the sun to flying a pure ballistic Jupiter trajectory with long wire booms. So as we've heard all this week, there are currently 3 options that we're looking at: an unpowered flyby, a powered flyby, and an unpowered flyby of Jupiter, followed by a powered flyby of the sun. The unpowered flyby would basically have a solid rocket motor, which is acting as a 3rd or 4th stage, which would be fired shortly after launch, after which we would separate from the solid rocket motor, and we would start to commission our spacecraft. We would start to deploy our booms, our science instruments, basically test out our system, to make sure that everything is stable and we're ready to proceed on with the rest of our mission. A powered flyby of Jupiter would delay all of that commissioning activity until after the flyby was complete. So we wouldn't begin to deploy any of our science instruments that are out on booms and stuff until after we separated from the solid rocket motor after Jupiter. And the Sun Oberth maneuver would require a large heat shield, as we've heard in previous talks. And so we could not be spin stabilized until after the shield was separated, and we could not deploy any of our science instruments until after we were outbound, probably past Venus or something at this point, because we wouldn't be in the thermally safe configuration to do that. So I just wanted to point out, for all of the options, the spacecraft pulls over 7 Gs during the SRM maneuver. So that's one of the reasons why you can't have any deployable structures while you're doing the solid rocket motor maneuver. So for a spinning interstellar probe spacecraft. This is the concept that the spacecraft is always spinning following launch. The spin rate will be driven by the science requirements. So scientists will tell us how fast we have to spin, and we will design our guidance control system around that and develop hardware as needed to support that science. Several trades are still currently underway, but it looks like notionally, right now, we are baselining a large, relatively fixed high gain antenna for communications. I say relatively fixed because I'm assuming there's the possibility of making adjustments to the high gain antenna bore site to help compensate for coning that we may occur. The driving requirement for the guidance control system is to enable high gain antenna bore site pointing or precisely enough to maintain a data rate to play back the science and engineering data. You have to be able to get the data to the ground for the mission to be useful. If you fly out to 1000 AU and you can't talk with it, it's not much of a, not much of a science mission. And the data rates are completely governed by how accurate that pointing is. You have to be a stable spinner during all phases of the mission. You'll have to be basically communicating through the high and medium and low gain antennas, even when you've got the solid rocket motor attached to the spacecraft. And in this configuration, having a very, very, very heavy mass at the aft end of your spacecraft might change what the major axis that you're spinning about is, unless you add something like booms or outriggers or something to ensure that you don't change the principal axis that you're spinning about when you separate from, yes, sir. So frequency versus pointing requirements. This gets into whether it's better to use X-band, Ka band, or optical communications. Basically Ka band is better up to a point in terms of pointing operations. The break-even point, as Rez had brought up in an earlier meeting, is around 0.079 degrees. Any further off than 0.079 degrees, you basically, the rates drop off of a cliff. It's even tighter for optical, as we were talking about. We're talking about nanoradians here as opposed to degrees. So we have chosen nominally a 0.02 degree requirement for the system design because I believe that this is something, a feasible requirement that we can meet with, without having to go to too many extremes so we're not becoming so creative with our system that we can actually fly it in a robust way. So here again is the sort of notional spinning spacecraft that we're talking about. We've got our high gain antenna, which is co-aligned as best we can to the spin axis. We have these long flexible antennas that we've been talking about. We have deployable magnetometer booms. We have 2 booms right now configured for symmetry so that we don't unbalance the spacecraft. We have 2 RTGs also balanced. Again, balancing the spacecraft is really key to getting the pointing that we need. We have a separation ring. We have 2 science booms so that we can have science instruments that can look out, out beyond the high gain antenna. Those are also balanced. It is, we don't know if those are going to have to be on deployable booms or if those are on fixed booms, but that's work to be done. And here's the separation ring where we would be attached to our solid rocket motor. So what are the primary effects that you would see in a spinning spacecraft? Well, there's 3 primary effects. You get the coning effects, nutation effects, and there we go. And then higher order modal frequencies. The coning effect is an offset between the major principal moment of inertia and the spacecraft body effect. So what essentially you see is the bore site of a body axis, in this case, the high gain antenna, which would cone around the principal moment of inertia if they're not aligned. And so as you get one spin revolution, you would see the high gain antenna motion sort of trace out this cone in space. It is totally dependent upon the masses of the spacecraft and how they are distributed. So if you put a mass off to the side, that's going to unbalance the spacecraft and cause some of this coning effect. As the spacecraft ages, this will change. Instruments are deployed, flexible objects will shift, and propellant is consumed. Those all change the moments of inertia of the spacecraft and will all directly affect coning. This could be compensated for by shifting the high gain antenna in the body axis. So you have some type of limited gimbaling system on this to slightly tweak up the high gain antenna dish. Then this is something that you can compensate for. It appears as a constant transverse body rate in the non-spin axis. So if you've got an IMU on board the spacecraft, you see this as essentially two non-zero transverse body rates. And as I said, the period of this, the frequency of this is on the order of the spin rate of the spacecraft. Nutation is an effect that you introduce when you apply a torque to a spacecraft that is spinning, such as a thruster performing a precession maneuver when you're trying to target the Earth. The larger the torque, the larger nutation. This is a transient effect that occurs and damps over time. The damping over time is based on the spacecraft's nutation time constant, and that is governed by the amount of energy that can be damped or removed from a system, usually due to friction between things like propellant in a tank and the tank walls itself, nutation dampers, internal wire friction, etc. All of these are going to suck kinetic energy out of the system, and that's going to cause it to want to spin about its major moment of inertia, because that is the lowest energy system. Momentum is constant for the system, but energy is not. Nutation frequency is defined by the spin rates and the moments of inertia, the off major axis moments of inertia. You want to be very careful with those because you don't want the nutation frequency to be a multiple of your spin rate. If it is, then you just by processing a spacecraft, you pump up nutation, which is not a good thing. So you have to carefully tune those IXX and IYY terms so that you don't get into resonance. Then you have, once you start adding flexible booms into the system, that's when things get really fun from a control standpoint. Higher order modal frequencies are introduced when a force or torque is imparted to the spacecraft. And then the flexible structures start to move with respect to the center of mass. This includes the magnetometer booms we talked about. This also would include propellant slosh and any long wire antennas that we have. It is also a transient effect that damps out over time based upon the internal damping of the system or the wire itself. The stiffer the boom, the quicker it dampens out, and long flexible wired booms take days to dampen out, as we've seen on Van Allen probes. So an example of coning. So this is something that we saw on the New Horizons spacecraft shortly after launch. All spacecraft are balanced, spin balanced very, very carefully on the ground. New Horizons was balanced basically with a mass simulator. And that'll be my first movie that I want to show. So let's try and see if I can bring this up here. And so if everybody can see the movie, you put it on a spin table and you very, very slowly rotate the spacecraft around the spin table. And what you're looking for is imbalances introduced by offset masses. When you sort of characterize what the mass distribution of the spacecraft is in this configuration, you start putting ballast masses in various locations. And New Horizons found interesting ways of adding ballast masses. There's quarters located. There's some of Clyde Tombaum's ashes located on various places. And I forget the number of interesting items that we've got spread around the spacecraft, but all of that was a clever way of trying to keep the spacecraft balanced. And these are like little 1 gram weights that are spread throughout the system. However, despite all of that diligence and rigor, we found out that the spacecraft New Horizons actually was imbalanced once we had launched. And it was imbalanced by approximately 0.25 degrees. And the primary reason for that was if you notice, we were not spin balancing with an RTG because it is very dangerous to have an RTG anywhere around a spacecraft. And so this RTG is actually loaded onto the spacecraft on the fairing very, very shortly, right before launch. And the people who are trying to do it are trying to be very, very diligent, but at the same time, you've got a very, very hot RTG and you're trying to not sit there and irradiate yourselves for too long. So what actually happened when they were mounting the RTG is it slipped a little bit. It introduced these off-axis products of inertia, and that introduced the coning. And that coning gave us an effect, sorry, it's over here, that looks like this from the New Horizons spacecraft. So in this particular case, the moment, the principal moment of inertia is perfectly aligned on the Earth, and this white circle is the high gain antenna beam width. And you can see over the course of 2 spin rotations what the high gain antenna is doing. So even if we are perfectly oriented at the Earth, the bore sight of the high gain antenna will never get closer than that coning angle. If we are off the Earth by basically half the beam width, then for half of the spin period, it is perfectly aligned with the Earth, and the other half of the spin period is lined off twice as far, and that's really, really bad for communications. So we want to minimize coning as much as feasible. Nutation, as I said, is a transient effect, and this is something that is introduced to the hub of the spacecraft anytime you do a torque. It damps out as a function of the nutation time constant, and those nutation time constants typically are on the order of 3,000 seconds to about 8,000 or 9,000 seconds for all of the various spacecraft that I've been associated with. I'm sure it varies from spacecraft to spacecraft, but it's sort of on those, hours time frame. Here you can see nutation damping on New Horizons. Again, New Horizons only uses propellant for nutation damping, and our time constant is around 3,000 seconds. Basically, after 3,000 seconds, we suck out so that the nutation at the end of it is about 37% of where it was, and that consistently damps out. Every 3,000 seconds, you're about 37% left, until all that you're left here at the end is essentially the coning that you were seeing, so the off-axis transverse rates. Then the third effect is the higher order modal frequencies. Now, when you introduce a force or a torque to a spacecraft, with booms, you introduce these 5 different modal frequencies that you see. The first 2, what are called jellyfish and saddle, those actually don't affect the pointing of the high gain antenna. It's these other 3, mutual precession, boom nutation, and hub nutation. Those are the ones that will pull the high gain antenna off of the Earth or whatever your target is. And it is this mode 3, mutual precession, which is a direct interaction between each of the booms and the main spacecraft hub, that has the longest time to damp. The period, you can see the periods here for a notional interstellar probe spinning at 5 RPM, and the period of mode 3 is on the order of 250 seconds per oscillation. And so what that's going to do is it's going to take a very long time to damp out. So here's a simulation. Like I said, we know a lot about the dynamics of flexible booms from Van Allen probes, and this is a direct post-maneuver analysis of the dynamics from Van Allen probes. And what I wanted to show you here was you can see the different frequencies on top of each other and how they damp out as a function of time. So you can see sort of the higher order frequencies here, and you can see them go away over the first 3,000 to 5,000 seconds. And so that after a period of time, all that you're left with is that mode 3. And that mode 3 persists for a very, very long time. This is actual data, again, from the Van Allen probe spacecraft after we did a precession maneuver. Each of these spikes is an eclipse period. where we basically went through, you know, behind the Earth, and the spacecraft cooled off and then reheated again. But you can still see the motion of those booms slowly damping over the course of days. So if you're doing frequent precession maneuvers on an interstellar probe where you're having to track the Earth every day or so with these wire booms deployed, then the problem is that you never let this motion damp out fully. And it can actually be an additive effect. So each maneuver after this can add on top of the oscillation that you already have, and they can sort of build upon each other. So that's something that we would need to take into account. So Van Allen probes had all of these maneuvers, and we were able to model it. I kind of wanted to show what that actually looked like. And here you can see, if you can see the green trace on the screen, this is at the end of a particular maneuver. And this is what all of those different frequencies look like when you stack them up and you trace essentially a notional high gain antenna in the sky. And so you would have problems communicating with the spacecraft until all of these transient motions damped out. You just wouldn't be able to, even if you were perfectly pointed at the Earth, which would be the center of this circle, you still have the high gain antenna pointed off the Earth. So, let's see if I can get that away. Yeah. So boom deployment. This is something that I would like to sort of discuss because there is a concept of what booms deploy look like, and then there's reality. And the sort of concept, and of course it's not on the screen. It's on my other screen, which I can't get to. So let's see if I can do this. Nope, that's done, sorry. Let's see, there we go. So this is a really lovely movie which shows what the spacecraft notionally people would think that it would be doing. Following an SRM separation, the spacecraft would be spinning, and actually the sun's to the left, so theoretically we would have to precess the spacecraft about 90 degrees at this point. But then the concept is, there go the booms, they just deploy out very nicely. And then once those are out at around 50 meters, you deploy out the magnetometer booms. And then away we off we go to the edge of the solar system and stuff. But the reality is that that's not what happens. What happens is anytime you deploy anything that's going to change the spin rate of the spacecraft. And so if you're starting a deployment off at 5 RPM and you start to deploy these booms, it's going to cause the spacecraft to slow down. So what you're going to have to do is you're going to have to introduce spin-ups throughout your deployment sequence. The other thing that you need to be very, very careful about is if booms become unbalanced, because any unbalance in an 80-gram tip mass at 50 meters is going to cause a significant amount of shift to your products of inertia. So following each deployment, you need to make sure that the spacecraft remains balanced, and you also have to make sure that the booms are deploying basically symmetrically. If they're deploying asymmetrically, then you need to stop, you need to think of what's going on, you need to troubleshoot, because most of these booms do not have retraction mechanisms in them. So this is a very long, intensive process that spans days, if not weeks. Basically, on the right here, this plot, this is a notional spin down maneuver where we were deploying the spin plane booms out to 15 meters. And you can see the first pair that goes down and then the second pair. And after each pair deploys, you have to make sure that the spin rate of the spacecraft is exactly where you think it is supposed to be. If it is spinning faster than notionally what you think it is, that means that one of the booms is not deployed the proper length. And then you have to sit back and you have to troubleshoot and figure out why the booms didn't deploy, and if you want to proceed to the next phase of deployment. During that time also, you're having to precess the spacecraft, obviously, to maintain the high gain antenna onto the Earth, which is going to cause a period of time where you're precessing in these intermediate deployment stages. So all of that has to be done very, very, very carefully. One-way light time, round-trip light time also has to be, accounted for. If we do it shortly after Earth, then the round-trip light times are pretty short, but if we're going to do it after Jupiter, then there's 100 minutes that we have to account for. And then we have to account for gaps in DSN scheduling, so you might be able to do 2 maneuvers, have to wait for the next DSN contact, and then proceed on with your deployment. So just sort of an overview of all the different challenges. Long wire booms obviously require spin stabilization to keep them taut. You have to be over a certain spin rate in order to keep the tension on them properly. So the spacecraft must remain over that prescribed rate during deployment and throughout the mission. Long wire booms need to be deployed symmetrically, obviously, so we don't get coning. Mass imbalances, of any mass imbalances, that leads to coning. And these imbalances can change after time. So even if you have a nominally deployed set of booms, everything's out at 50 meters, as the spacecraft ages, those moments of inertia shift over time. We've seen that over a 6-year lifetime of the Van Allen probe's missions. Booms can break. We talked a little bit about it earlier in the week, but several spacecraft that have launched and have booms like these, they have had failures in those booms, whether the tip mass breaks or the entire wire boom breaks. And I'll give you an example of that in a couple of slides. Booms increase the propellant usage throughout the mission by increasing the system momentum. So as you deploy booms and the system momentum goes up, it takes more propellant each time you want to precess the spacecraft. For example, the New Horizons spacecraft uses about 100 grams of propellant per year to track our high gain antenna to the Earth. If you have your system momentum 7 times higher than the New Horizons spacecraft, then you're going to have to use 7 times as much propellant notionally. So you're using about 700 grams a year or about 7 kilograms a decade, which adds up over time. Boom motion will decrease your downlink rates until those booms have damped. The more frequent the precessions, the less time you have the booms to be damped to get the highest data rates that you're hoping to get out of the spacecraft. There are 3 papers out there for Van Allen probes that describe the boom nutation. All 3 are very, very good. They're very detailed, very technical, but it is this paper, AIAA 6203, written by Tim McGee, which describes these modal frequencies in great detail, and you can see how they change as a function of mass properties, boom lengths, boom masses, spin rates, etc. I tried to take all of that information and compile it into a single presentation, which will be coming out later in March in 2021 at the IEEE conference. So let's see, some assumptions for wire boom deployments. I want to just give you how the spacecraft would notionally change as you start to deploy science instruments and wire booms. If we assume that the hub of a spacecraft, and this is about the same moments of inertia as the Van Allen probes, is on the order of IXX, IYY, IZZ. These are the 3 principal moments of inertia. And we would be spinning about the z-axis, so you want the IZZ to be the largest of the 3. If you start off with everything perfectly balanced and you have about 500 kilogram meters squared of inertia about the z-axis, and then you deploy a nominal set of EFW wire booms, and here's sort of the properties of those. What's going to happen is as you deploy those booms out to 50 meters, you're going to see the major moment of inertia increase to around 2,700 kilogram meters squared. And then if you were actually wanting to go out to 100 meters for those booms, you are well over 11,000 kilogram meters squared. So all of that extra inertia you are going to then have to compensate for when you're precessing your spacecraft. So that's going to increase all of the propellant that you're going to need to maintain control. And then here's just examples of what would happen if one of those booms had an anomaly. Here's just 3 notional examples. And remember, we have a 0.2 degree requirement on pointing our high gain antenna. So if all of them deploy perfectly, then we have no coning. But if one of the booms loses its tip mass, just the mass at the end of it, the rest of the wire is deployed just fine, you introduce 0.28 degrees of coning. So you're already exceeded the requirement for pointing the high gain antenna. If you are deploying the booms and one of the booms gets stuck at, in this case, I put it at 22 meters, but all of the remaining booms deployed out to the 50-meter point, then you introduce 0.325 degrees of coning. So again, that's even worse. And then if you were carefully trying to monitor the booms as they deployed, and you got an imbalance of just 5 meters between two booms, so two booms are only off by 5 meters, that introduces 0.1 degrees of coning. So you would basically, half of your pointing capability would be lost due to that particular anomaly. Why are we concerned about that? Because missions in the past have had failures. Image is an example that's been used in the past of a spacecraft that could deploy booms out to 250 meters, which they did over the course of a month, and they were spinning at about a half an RPM. But then 7 months after that deployment, the -X boom lost 130 meters of length. 11 months after that, the -Y axis lost 25 meters of length. And then 11 months after that, the +Y axis lost its tip mass. And finally, 13 months later, the +Y axis lost the entire remaining point of the antenna. So this thing was shedding antennas throughout the course of several years, which any one of those would have been catastrophic to an interstellar probe. Themis, that was a group of a cluster of spacecraft. One of them had a tip loss mass. The FAST spacecraft, that also had booms, one of them did not deploy properly. MMS and Van Allen probes. Van Allen probes had 2 and MMS had 5 spacecraft. All of those booms deployed properly, and I don't have much information on MMS, but I do have information on Van Allen probes after the boom deployments, and I will say that the coning angle changed over the course of the mission. And it was not related to propellant usage, it was just aging of the spacecraft. We saw the introduction of dynamic coning. And I'm going to say dynamic because it changed as a function of time. So again, coning can shift as the masses move about the spacecraft, as these booms have been extended and are flying through many years. Some booms stretch, some booms contract, they relax or tighten. It is random in the way that they do that. And similar shifts could affect the high gain antenna in the spacecraft body frame. So it actually, we see twists occur in the spacecraft body over time, small twists that we can measure in the sun sensor data on Van Allen probes. So there were 2 types of shifts that we saw on Van Allen probes throughout the life of the mission. The first was the migration of the period between the sun sensor heads. So there's 2 sensor heads, A and B, so you get 2 pulses per spin, and you can closely measure the time between pulses. If these are perfectly 180 degrees apart, then you should see a pulse, and then it goes around 180 degrees and you get another pulse. But if they start to shift in the body frame, then the timing, the relative timing between those pulses changes. And you can see the migration of the time over the life of the mission. It starts off close to about 180 degrees, but shortly after launches, the red line shifts down by almost 0.3 degrees. Then it shifts up over the course of several hundred days, remains relatively constant for out to about 1,500 days after launch. And then for some particular reason, we have no idea why, there was nothing that was done differently in the mission. It was not targeted to any propellant usage. The 2 drifted off by a full degree. And then they started, for whatever reason, coming back in. This was just, the RBSP was doing the same thing in different ways at different magnitudes at different times. So it wasn't correlated, both spacecraft were identical, it wasn't correlated to any phase of the mission, it was just how the spacecraft was aging. We were also noticing changes in twist between the 2 sun sensor heads. So early on in the mission, we were seeing, about a year after launch, the twist can be seen as these humps that occur over these 21-day time frames. The more twist, the larger the hump. Early on, RBSPA had a large twist. RBSB was more flat. And then over the lifetime of the missions, the twist shifted. So, and you can sort of see just how all of these effects change over time. That's something that would have to be dealt with for an interstellar probe spacecraft. You have to deal with the aging of the booms. So just a few summary of the challenges for having these long wire booms. It's going to take more propellant to deploy them to a significant length. It's going to take a long time to deploy them, especially if we do this after Jupiter. It's going to require constant monitoring of the spin axis of the spacecraft to basically compensate for migration of the moments of inertia. Data rates will decrease until nutation rates and higher modal frequencies have damped out. So we can't do a precession and then instantly talk with the spacecraft. We will have to let things damp out before we're able to communicate at the highest data rates. And failure to fully deploy wires or a break in a wire could endanger all Group 1 science or the mission if the data rates are too low to play back the data. So if we lose, if our pointing is now 0.4 degrees, how much data can we get back down on an X-band antenna? They are feasible. I'm not going to say that they're not feasible, but they are definitely a challenge that we want to carefully weigh when we're designing this mission. And we also have to consider the frequency that we want to do maneuvers and DSM contacts around to compensate for nutation. So this is just tracking the Earth. This is the notional, how much would you have to precess the spacecraft to maintain tracking on the Earth? It obviously decreases the further you get away. So by the time you're in the Kuiper belt, you're only moving on the order of maybe 5 to 10 degrees a year. And then as you get out past 2050, it's only on the order of 2 degrees a year, but you're still having to track the Earth back and forth as it moves in its orbit, and the spacecraft moves sort of sideways with respect to it over time. So now a dual mode spacecraft. So talking a little bit about a New Horizons type spacecraft or a 3-axis only concept. I'm only going to briefly touch on these because most of our work up to this date has been for the Heliophysics mission for Interstellar Probe. New Horizons spacecraft spins at 5 RPM for most of the time. It spins down to 3-axis mode for planetary flybys and distant Kuiper belt object observations. After that, it spins back up in order to downlink the data and to save on operational life of the spacecraft. When we're in spin mode, we can power off the guidance control system for significant portions of time and just use the basically inertial pointing to downlink. It's inherently increases the lifetime of the mission. It reduces the amount of propellant that we have to use over time, and it reduces the amount of cycles, open and closed cycles on the thrusters that we have over time. By contrast, Voyager has remained exclusively 3-axis mode for the entire time that it has been flying. It does this because it has very, very large moments of inertia relative to New Horizons, and so it remains very still for most of the time. And it is able to point to its targets by use of an optical scan platform, which is over here on the left. So the spacecraft itself remains, the body remains inertially still, whereas New Horizons has to reorient itself for each of the observations. And so this is what a flyby, if you can see this, of New Horizons was for Pluto. You can see how the spacecraft has to frequently reorient itself, which you're able to do because it's a very compact spacecraft. It doesn't have flexible booms out there, like even sort of rigid flexible booms out there, which would increase the moments of inertia. And frankly, I just wanted to show that because I love that particular video. So, sorry. Let's move that off. Whereas I was trying to get a comparable video of Voyager flying by Neptune, where it remained with the high gain antenna pointed back to the Earth, and the scan platform was oriented to point to the body, and then cameras were slewed across the various targets. So some considerations for dual and 3-axis mode. We still need to use thrusters for control. We've talked about this earlier, but reaction wheels would not last for 50 years. And even if they would last for 50 years, they are very, very power hungry. You need at least 80 watts to keep 4 reaction wheels running for a significant portion of time. And so that would be a big chunk of the power budget. Propellant used is a function of the number of times you spin up, how the spacecraft is controlled during the encounters, and how much downlink is conducted in 3-axis mode. Downlink in spin mode is cheap, but downlink in 3-axis mode is expensive. So the more time you want to spend in 3-axis mode, the more planetary flybys you want to have, the more propellant is going to take. And those would be trades done by the science team. Thrusters can fail over time and usage, so you need to be very careful how you use them. Voyager has given us a good example of how long typically thrusters can last. Cassini also has given us some data sets. So we do know how to actuate these thrusters over time. We just need to be careful with how we would use them. Dual mode spacecraft can power off GNC sensors and processors while in spin mode to extend the lifetime. I already talked about that. However, we could not use long flexible wire booms. We would have to have shorter Voyager style antennas and magnetometer booms. We would have to move less aggressively than New Horizons does, which could determine how we actually do a flyby encounter. And we would have to basically assume that we're going to use more propellant per maneuver because the moments of inertia would be higher. A spacecraft in 3-axis mode could compensate for any shifts in principal axis just by changing the pointing of the high gain antenna. That's the best thing about 3-axis mode, is you don't have to worry about coning and all of the boom mutation. You could just target the high gain antenna to Earth as best as your thrusters can provide, and then downlink the data. And an all 3-axis mission has large science implications because heliophysics would not be happy. They like their spinning spacecraft. Tracking during a flyby, and so I already showed the movie about us flying by, and but tracking is right now both Voyager and New Horizons are open loop targeted systems, which means there's not feedback from the science payload in order to target the pointing. So we would have to basically use optical navigation in order to tell us where we are, so that we could accurately target our cameras for any flybys. And I already talked about the movable scan platform, so I can just go now to Sun Oberth. Jim actually had a really good talk about this, so I don't want to go too much into detail about it, but the biggest concern we have is as you fire off the solid rocket motor, you are going to get a large center of mass off shift towards the shield. And it is going to be on the order of maybe up to a meter or more, depending upon how much your shield weighs and how close you get, and what your rocket motor is. We cannot compensate for that with thrust vector control. You would need a very large supplemental system, or you need to add a lot of ballast mass. So you minimize the shift of the center of mass towards the shield. The heavier the shield, the more the migration. Some other considerations for Oberth spacecraft, as I said, needs to remain 3-axis pointing. The shield prevents communications in certain direction, and the solid rocket motor itself would prevent instrumentation in certain directions. So you need to be careful about that. Supplemental thrusters are going to need to be added while the stack is in place. We just, most of the thrusters for the spacecraft are going to be hidden behind the shield, and so you need to have a supplemental thruster system. You have to have redundant processors and sensors, which reduces the overall efficiency because more mass means less velocity. You want to have gobs of redundancy, because if you mess up your pointing for more than a few seconds, you've basically melted your spacecraft. And it only has to be a few degrees that you have to be off before you can get into real trouble. And then, so GNC hardware development will be needed to support a Oberth maneuver at the sun. You need to have star trackers that can work at those ranges because background noise is higher. High energy protons are higher. That's going to fuzz up the cameras. There's lots of reasons why star trackers do not like to be near the sun. Sun sensors the same way. Any sun sensor only works when it's in the sun, and so you have to keep it out of the sun most of the time, and it has to be survive enough time in the sun so that it gives you valuable data so that you can correct any pointing accuracies you have. So there's going to be a lot of work that would need to be done in hardware development for that. So some lifetime configuration issues, how to design a 50-year mission. You need to limit the consumables you have. You have to design a system that minimizes the amount of propellant that is needed for the mission. You have to be very conscious of the operational hours that you put on your hardware. Hardware like IMUs and stuff degrade over time, with the exception of hemispherical resonating gyros. Most other IMUs have a life-limiting feature, so you have to keep them off. Keep it simple, robust. The more bells and whistles you add to a system, the more places failure can crop up and can really hurt you. Limit moving parts. Gimbals, reaction wheels, slip rings, mechanical gyros all degrade over time, so we should limit the usage of those in the design of our system. Obviously, adding fully redundant hardware as much as we can will increase our lifetime. Each extra component adds mass, but a cold sparing system greatly reduces or improves our robustness and will improve the chances of full mission success. Keep software simple and up to date. Glenn was talking a lot about this. The more complicated the flight software, the faster it will go obsolete. Don't come in with a very sort of fancy flight software package. Keep it simple. If you can design it in C, that seems to have a long history, that might be good, or as close to that as possible. And then have a personnel transition plan. Obviously, none of us are going to be here, or most of us will not be here working at the end of this mission. So everything from documentation of the very simplest parameter upload and why you would need to do that needs to be detailed, trained, handed over. GNC designers are sometimes not really great at doing that, but they're going to have to basically do that in order for knowledge transfer. So just some conclusions and takeaways. Driving pointing requirements is maintaining the high gain antenna to the Earth. Secondary requirements for planetary flybys or to support these very large TCMs need to be considered, but ultimately we need to design a system that can get the science data back to Earth. For a spinning spacecraft, that is all about balancing the masses and keeping those masses balanced as much as feasible. I would like to say a spinning spacecraft cannot support KA or optical communications. I know we've been talking about that previously, but I don't want us to fall off that cliff, that 0.079 degree cliff or a 10 nanoradian cliff where you get something that shifts and then you just have a negative acquisition, because those are bad days. Long flexible wire booms add risk, and again, more complicated, the more massive the GNC and the slower you're going to go. So, thank you very much. Questions?
Okay, Gabe, thanks very much. This was some really good stuff. We do have a few things over in the chat. I want to just kind of run down with you, and then we'll open it up for more. Let's see, Wayne asked originally, at what distance is the boom damping cause catastrophic pointing error if this is below 100 AU? And I think after some discussion, I think the question here is where the booms are deployed. Is there a point of no deploy because the damping will cause too many problems?
So once you start to deploy them, so once you get out to sort of say 5 meters, you're starting to see those products of inertia shift. And you actually have to really jump out to about 7 meters, I think, to start the whole process, which is one of the deployment mechanisms for these things. Is they sort of release to about a 5 to 7 meter deployment. And once they're at that point, that's when you can slowly start to spool them out. That the centripetal acceleration and tension on them that's when the deployment mechanism works. Once you get to about 10 meters or so, you're starting to see all of these effects increase, and you're seeing those shifts. So if one of them doesn't even deploy, like right off the bat, and the other one's out to 10 meters, that's going to be enough to throw you off by probably 0.2 degrees, and that depending on our antenna, that's going to be catastrophic.
Okay.
Yeah. So, Gabe, just that, like, the intent of the question was more at what point during the mission, as in like what distance from the sun, is that pointing going to throw you off to you can no longer talk to your spacecraft?
Right.
Somewhere after Jupiter. So Dave and Reza showed sort of how the medium gain antenna falls off as a function of time. So you could theoretically get 10 bits per second probably on the medium gain antenna out to Pluto type distances.
Right.
You won't be able to get science data back, but you would at least be able to sort of recover the spacecraft and be able to talk to it. Mm-hmm. But once you start getting out into those distances, then your medium gain antenna just essentially falls off of a cliff, and you're reliant upon the high gain antenna. And
right.
So, yeah. Where this matters is whenever we start talking about deploying after a Kuiper belt object flyby, for instance.
Yes.
Right. So that may not.
So if you deploy after a Kuiper belt, you are totally reliant on your high gain antenna for communication.
So actually, this might be one thing to take a look at in the telecom work. Is that thus far we've just been looking at nominal cases. We should probably look at safing data rates, and with the assumption that if we go into a safe mode, if something has gone wrong, we're on the MGA.
Yep. So we just encountered one of those, but on the high gain antenna for New Horizons, where we had to live through the weekend on 10 bits per second. Actually, I had to live for about 4 or 5 days on 10 bits per second.
Oh,
and I can tell you, recovery at 10 bits per second is very, very, very painful.
Mm-hmm.
Yeah.
So
that round trip light time.
Yeah. So one of the lessons I'm getting out of this is that we may want to go back and really decide whether a long delay in these wire antenna deployments is really a feasible thing or not. And so maybe it moves off the table, right? This idea that we could do a KBO followed by some sort of deploy.
Yeah.
Okay. Let's see what else. You mentioned that a number of missions have had booms and antennas to fail. So Vikas was interested in what might be the cause of these failures. One of the things that occurred to me was things like debris impact, micrometeoroid impact. Are there other causes that might contribute to this?
So FAST didn't deploy because you got overwrap of the wires. Okay. So essentially, if you lose tension on a wire and then retension it, if you've ever been sailing and you get sort of those overwrap of the lines and stuff like that, then once you put tension back on that line, there's no way to take the tension off of it. And so it will not deploy anymore. It just gets tangled up. So that's what happened to FAST. The break-in, I'm not sure about why image would break off in such random directions. Themis, they said it was probably a micrometeoroid impact, but the fact that you just have these wires, it just could be that the wires are too thin, they aged improperly, the metal became brittle. There could have been stresses on the booms after a period of time could have fatigued the wires. I don't know all of the different ways, but it's just something we would have to think about. You have to make it hefty enough that it doesn't break, but then as you add mass, that's going to increase your moments of inertia.
Yep, so. And also issues with things like jamming and things like that. Yep.
Yep.
All right, let's see, what else? There was a question about whether we could use heat sensors for GNC during the solar Oberth maneuver. So essentially, you have a temperature sensor out there that would detect an off-pointing. I think in this case, the time constant of a temperature sensor is probably too long to really be useful for.
Yeah,
is that right?
I think you're 100% right on that. I think that if you had something out there that was just trying to look at heat, it's going to go up obviously exponentially and then sort of fall off. But yeah, I think the time constants of that are much too long for what we need to do when we're at those distances.
Yeah, but I think the other issue is that I don't know of any temp sensor that you could fly that would be allowed to be exposed to direct sunlight. So maybe what you're looking at is a solar fuse rather than a temp sensor. So if you were to try to implement something like that, you'd have to put that temp sensor under some sort of material. So it would probably be on, for instance, the bottom side of the heat shield or embedded in the heat shield somewhere, which would just add to the time constant even further, right? So,
Yep.
Okay, I think that's everything that I saw in the chat. So at this point, let's just open it up. We've got a small enough number of people. If people just want to open their mics and fire away at Gabe, I'm sure he can handle it.
Hey, Jim, this is Ralph. Actually, I did have a question in the chat. And I'm not quite sure who this is for, but looking at image, sounds like it didn't do too well on these wire booms on the lifetime. And I'm just wondering, is anybody, how long has one of these wire booms actually lasted on a spacecraft? Or is the long, I mean, on some of these, perhaps the mission shut down before the booms broke off, but I'm just wondering what we've got data on.
That's a good question. I know Van Allen obviously lasted 6 years, but obviously they were deforming or changing over that 6 years. I think MMS launched after us, so they don't have enough, as much data, I believe. And Themis obviously, only I think 2 of them were active. They turned into Artemis.
Right.
When they went around the moon, and one of those 2 was the one that broke. So we definitely have data that one that's been out there for a while did have a break.
Mm-hmm.
Okay, I was just curious. Thanks.
So one of the things that may contribute to that is just thermal cycles, right? So especially with Van Allen, you're heating and cooling, and so there will be changes in the material. That's less likely to be the case for us. Even with the Solar Oberth maneuver, we would not have them out. So, you know, so thermal cycle associated aging effects would probably not be relevant, but there still are probably material degradation issues associated with just bulk temperature and things like that that we'd have to worry about. Yeah,
there would definitely be a big study that would go into the properties of that wire over time.
Yep.
Just for reference, I looked back. So the antennas on Voyager are 10 meters and the mag boom is 13. And I went back and I looked, and Voyager basically in the mag rolls does a 360-degree revolution in about 20 minutes. So
that's pretty speedy.
Mm-hmm.
What was the fastest that New Horizons maneuvered during the encounter? You were showing the film. Do you know?
We would do slews at 1.5 degrees per second maximum, because any higher than that, the star tracker started to drop out. Most of our science observations were on the order of anywhere from 2,000 to 3,000 microradians per second for the sort of the scans with LISA and MVIC and stuff like that. LISA actually liked to be much slower if it could be.
So a degree per second is
about 6 minutes.
I'm up to 360 degrees, right? Or 360 seconds for
one revolution, yeah. So
okay.
So yeah, they're probably moving around 0.5 degree, 0.4, something like that.
Well, the point is, it's still quite a bit faster than Voyager.
Mm-hmm. Yeah. Yep. And once you get moving, the spacecraft, inertia is your friend. You basically spin up to that rate, you stop firing thrusters, you let it go through one full rotation, and then you fire thrusters at the end to slow yourself down.
Right.
Yep, sounds good. Any other questions? I think that's everything from the chat.
So I would like to say, again, reiterate one time, these are challenges. I don't want to dissuade anybody from anything, but I just wanted to bring those to people's attention so they know what we're dealing with when they say, hey, let's deploy 250 meter booms at 100 AU.
Yep, absolutely.
I think this has been really helpful, Dave, and you know, it's mass, risk, and cost, right?
Yep. And that's all on Jim's plate.
Or Gabe, sorry. I'm multiplexing way too much these days.
Yeah. Okay. All right. Anything else for Gabe then? Yeah, Gabe, I would agree. I think this is really illuminating, and I'm looking forward to seeing the paper. I know I've read an early version of it, but I would recommend folks to go back and to go off and look at that Big Sky paper when it comes out. The IEEE Aerospace Conference. It's quite good, and I think it really helps to understand some of these things. All right. Well, I think that if there's no more discussion or comment, we could probably go a little early and give people a chance to take a little bit of a break. Andrea did ask me to remind folks that we do have our poster session in Gathertown coming up. And I'm just now putting the link to this in our chat window. So feel free to click on that and it'll take you over there. I think we've got some really interesting posters that are going to be fun to look at, I think. And with that, I'll give one last opportunity for folks to jump in. And if nothing, then we'll go ahead and take a break. Okay, sounds good. We'll see you at the poster session. And
thanks again, Gabe.
Yep, glad to help.